I'd like to welcome you all here on behalf of Wycliffe College, the Meeting House, and for this special edition, the Canadian Scientific and Christian Affiliation for our pub night this evening. I'm pleased to welcome Patrick Franklin, Professor of Theology at Tyndale, and Dr. Barth Netterfield, astrophysicist extraordinaire here at University of Toronto. And they're just going to have a little informal conversation about all things in the universe. I think that's what's fair game when it comes to astrophysics, right? Everything. Yeah, it could be a long night, but I'm sure you'll make it interesting, right, Bart?
Maybe even some things outside of the universe.
Maybe. That's where the theology comes in, right? So we're just happy to have both of you here, and I'll just turn this evening over to you guys, and we'll join back later. Feel free to get more beer as the evening progresses. Thank you, everybody.
Perfect. So I'm coming here primarily as a representative of the CSCA, the Canadian Scientific and Christian Affiliation. We're a network of scientists and those interested in science who also share Christian faith and often explore questions that come up in the midst of that intersection between faith and science. And we're present at many universities in Canada, and we like to do some things with churches as well. And so we've got some literature in the back if you're interested in checking us out. And there's some documents out there on some issues. We're trying to do more issues-related pamphlets, sort of like, creation and climate change, or what do Christians think about creation and things like that. So check those out. Bart, can I call you Bart?
Sure.
All right.
Hi, Patrick.
You can call me Patrick. Perfect.
Or we just call each other Professor. That'd
Professor.
Be weird.
We could do that.
That'd just be weird.
I don't know if you ever saw the movie K-Pax.
No.
I might be like anyway, it's Kevin Spacey, and he meets these doctors, and they're all like astrophysicists and stuff. And so he's in this line, and there's like 6 or 7 of them. He's like, doctor. There's a lot of doctors on this planet.
Okay.
Anyway. Well, okay, so I've heard a little bit about you. I hear stuff about balloons,
Yes.
boomerangs, and the Antarctica.
Yes.
So like you throw boomerangs in the Antarctica. Is that what you do for a living?
Sort of.
Sort of. Okay.
No.
Well, let's back it up. Have you always been interested in science?
Yeah. Well, originally I was interested in dinosaurs because, after all, I was a grade 3 boy. That's what, as far as I can tell, grade 3 boys do. It was fantastic. I love dinosaurs. But then I kind of got interested in airplanes because they're cool and they go fast. But then I found out that aeronautical engineers don't design airplanes. They just design a small part of an airplane. And I learned about relativity and decided that physics is way more fun. And then that was like grade 10.
And it was off to the races from there.
Yeah.
Well, I might have a son who's treading in your footsteps.
Okay.
When he first went to kindergarten, he came home after school and he said, "Mom and Dad, teachers at school don't know anything. I asked them how to build an airplane, and they couldn't tell me. What's the point of going to school?"
Well, that's a good question.
It's a very good question. So, okay, well, this stuff that you do, let's talk about that a little bit, because it's really intriguing.
Yeah.
The stuff that you do with balloons and the Boomerang project and so on. You want to talk a little bit about that?
Sure, absolutely. So there's a couple directions we can go. One is I can talk about some of the things we found out, and I will tell you that, because that's really cool. And the other is just sort of how we do it. So
Perfect.
I guess then we'll start with the first one, which is what do we do? It turns out that the atmosphere absorbs some kinds of light. Microwave light, for example, it gets absorbed by the atmosphere, particularly water vapor in the atmosphere. And so if you want to do a really good job observing space, you'd like to get out of the atmosphere. You can go on a satellite, but that's, $1 billion. So it turns out NASA builds these balloons which can take a 3 or 4 ton telescope to an altitude of 35 or 40 kilometers, which is basically above 99.5% of the atmosphere. So it's 200 times less air above you there than on the ground. Mm-hmm. And that factor 200 is good enough so that you basically can ignore the atmosphere. So we build telescopes, we hang them from balloons, and fly them from places. So Antarctica, for example. Imagine you go outside with a balloon, a party balloon, and you let go, and it goes up. And as it goes up, the air pressure around it goes down, so the balloon pops, right? So that's no fun. So you take your telescope and you put a balloon on it, and you launch it, and up it goes and it pops. Nope. Terrible idea. So instead, you only inflate it 0.5% full. So it can grow by a factor of 200. So you launch your balloon, and up it goes. As it goes, it expands and expands and expands until finally it pops. Nope. Bad idea. Okay. You put a vent on the bottom of the balloon, so when it gets overpressured, it'll vent out. You launch your balloon, and up it goes, and it goes up and up and up until it's full, and then it vents, and then there you are at float altitude. So imagine you launched at dusk when the winds are calm. Up it goes, flies along all night. Sun rises, shines on the balloon. Warms up the gas inside the balloon. The gas expands. It pops. No, you had the vent in the bottom. Psst, let's spit out, flies along all day. Hooray. Sun sets, gas cools, your balloon isn't full anymore. That was a fun flight. So if you want to stay up for a long time, you really need to get rid of sunsets. And the best way to get rid of sunsets is to go to Antarctica in the austral summer, where it's 24-hour daylight. So we can launch a payload from McMurdo Station on the coast of Antarctica, and the winds will actually blow it around the continent. It's just winds just go around and around. And our longest flight's been 18 days, but only because our detectors ran out of cryogens. But there's been flights down there that can go a couple of months. So it's a pretty great thing. It's dramatically cheaper than a satellite, but you can get some pretty great science out of it.
And so down in the Antarctica, you're saying it can circle around and around, and you can try to retrieve it. Yeah, you
basically go out with airplanes and land on the ice and put it in the plane and fly it home.
Very good. So the primary reason for the balloon is cost. That's the main.
So you want to get out of the atmosphere.
Yeah.
And it's cheaper than a satellite.
Okay.
And so one of the reasons we do it, if you care about public policy, maybe you don't, but maybe you do, is to train students on how to work on payloads in a space-like environment. Then hopefully they go on and work in the space industry and make satellites. So.
Okay, and so and the reason you're putting these satellites up there is to detect types of light we couldn't otherwise see.
You couldn't, or be very difficult to observe from the ground. So, so then the other side is like, what sort of things are we looking at over the years?
Yeah.
So some of the experiments I'm working on have been looking at a thing called the cosmic microwave background, which you probably don't know what that is. No, good. Everybody's like, no, but I won't tell you that I don't know, because maybe I'm supposed to know. No, you wouldn't know. Okay, so here's how it goes. Let's see. Let's look, if you look out in space and you see a galaxy. You know what a galaxy is? It's a cloud of 100 billion stars. So you see a galaxy. If you look at a galaxy, you'll see that it's moving away from us. And if you look at what's further away from us, it's moving away from us faster. And actually, the further away you see a galaxy, the faster it is moving away from us. Well, that's kind of interesting. Put that on the shelf, just as a thing to know. We'll come back to it. It also turns out that light takes time to travel. So when I look at something, I'm seeing it like it was in the past. So I look at you, I see it like you were about 10 nanoseconds ago. Okay, well, yeah, that's great. That's awesome looking into the past there. Who cares? If I look at the sun, we see it like it was 8 minutes ago. It takes light 8 minutes to get here. So imagine the giant monster from Star Trek eats the sun. We don't see that happen for 8 minutes. Okay, cool. Look at the nearest star. You see it like it was 4 years ago. Look at the nearest galaxy. We see it like it was about 2 million years ago. So we have no idea we don't. Okay, we have an idea. We don't know what the Andromeda galaxy looks like now, except to say probably similar to what it looked like 2 million years ago. But we see it as it was 2 million years ago. When something happens on Andromeda, like a supernova, we see it happening 2 million years ago. We don't see things happening today, right? Looking into the past. The farther away you look, the farther back in time you look, because light takes time to travel. Okay, so universe, we can look farther away, look back in time. Galaxies are moving away from us. The universe is expanding. That's interesting. So if you look further and further away, you look back in time to when things were closer together. right? The universe is expanding. So in the past, things were closer together. So you look at some distant galaxies, and you see the galaxies are close together. And look further away, they're even closer together. Okay. So the universe is expanding. Now, there's a thing they're probably getting wrong here, because everybody gets it wrong, because every time I've ever seen any presentation of this done, it's explained wrong. So unless you're somehow magic, you're wrong.
So pastors take note here.
Yeah, okay.
Yeah, no.
So, yes, for example, we had this picture here of the universe expanding, right? You have an edge of the universe in your head, don't you? Well, what's after the edge?
Oh, I was going to ask you that tonight.
There is no edge.
Perfect.
Right? So what you want to imagine the universe now is like I stop, look around the universe, what do I see? Stars, galaxies, clusters of galaxies. Okay, good. Move faster than the speed of light to wherever you want in the universe. Stop, look around, what do you see? Same thing. Right? No matter where you go, same thing. Now, all those galaxies are moving away from us. But in a way, like, so if I look at a distant galaxy, I say, it's moving away from me. But if I jump onto that distant galaxy and I look back at Earth, I say, oh, well, the Earth is moving away from me. So who's right? Well, neither. It's relative. Relativity, relative, right? Got it. Good cousins. Okay, so the universe is expanding. It's getting less and less dense. There's no edge. Just everything's moving further and further apart. Now, what happens if you take a gas? Well, the universe is kind of like a gas. Take a gas and let it expand. Well, it cools. If you compress it, it heats up. Let it expand, it cools. As a refrigerator works. Gas in your fridge expands, it cools the fridge. Compress it, heats up. Okay, whatever. Okay, universe is expanding, and therefore it's cooling. So if I look further and further away, looking further and further back in time, to when the universe was denser and hotter. Is this getting boring yet? No? Okay, good. So you look further away, you get further back in time to when the universe is denser and hotter. Now the universe is transparent today. You can see, there's no reason, you can see as far as you want. So I can look as far away as I want to when the universe was as hot as I want, I guess. Well, what does really hot gas look like? Like really hot. Yeah, or the sun, right? The sun is basically really hot hydrogen and helium gas. So if you're following my story, you should expect to be able to go outside and look at the sky in any direction at all and see the whole sky glowing like the surface of the sun. Has anybody ever seen that? No. But that's what you should expect to see. Do you see why you should expect to see that? Right? Doesn't matter. Whatever's behind it, look far enough in that direction, they'll see where that part of the universe in the distant past was really hot, dense glowing plasma. Now, we said that the universe is expanding, and the farther away I look, the faster things are moving away from us. Well, this plasma is really far away, and therefore moving away from us very fast. So a fire engine comes by, right? Or the jet. Or like I can make a few more sounds, we get the idea. Like a crying baby. Okay.
You would have been good at feeding your children, I imagine.
Okay. Well, light's a wave, and so if the source of a light is going away from you, it goes to lower frequencies. Instead of being, say, bright yellow light, it will get Doppler shifted to be red light, to be infrared light, to be submillimeter light, to be microwave light. So now if you're following my story, you should expect to be able to build a microwave telescope and point it at the sky and look in any direction, and you should see the whole sky glowing with this primordial plasma. And in fact, that's the case. It's one of the things we do is we build these telescopes, fly them in balloons, look in any direction you want, and you will see this hot glowing plasma, which is basically looking at the universe as it was about 13.7 billion years ago, or about 300,000 years after the Big Bang. So just a smidgen after the Big Bang. And by looking at this plasma, you can tell what the universe was made of then. And because of that, you know what the universe is made of total. We discovered, so from this, we actually able to get the age of the universe, the geometry of the universe, and the content of the universe. The content being mostly dark energy, which nobody understands what it is, but it's some magic thing that makes the universe's expansion speed up. Other than that, we have no clue. The next biggest chunk is dark matter, which is particles you can't see, smell, touch, taste, or any other way detect, except for by their gravity, which is maybe not surprising we've never detected them because you can't. So something like, wow, this is so mysterious. Like, really? Like, why wouldn't there be uncharged particles? Well, there are. So I guess that the answer is that there's no answer to that. And the last bit is a little sliver, 5% of normal matter that we can detect.
It's incredible. So 95% of what's out there
we didn't know existed until we did experiments like this.
Incredible.
So it's pretty cool.
So, I mean, one of the things that you're able to see and establish fairly clearly is, you just mentioned the age of the universe. You also, I think, talk a little bit about the geometry. How is that significant, the shape of it?
Yeah, that's interesting. So, anybody have the privilege of taking geometry in high school? Awesome. Anybody remember Euclid's axioms? Or that they existed? You're proving stuff from geometry. So, one of the is about parallel lines. And what's cool about parallel lines? Parallel lines neither converge nor diverge. Okay? Only if you're in a geometrically Euclidean or flat universe. Right? So if on a tabletop and you draw straight lines, absolutely, that's exactly what happens. Let's say instead you're on a sphere and you draw straight lines on the sphere, say starting at the equator. What happens to those lines? Well, they cross. Right? So straight lines converge. Or if you're on like kind of a weird saddle shape called a hyperboloid, something or other, I don't know, parallel lines diverge. Now, according to Einstein's model of general relativity, which we think is completely right, as far as we can tell, the geometry of the universe depends on its density. There's a magic number if, call it 1 in the right units, 1 Einstein or something. If it's less than 1, parallel lines will diverge. We live in an open universe. If it's greater than 1, we live in a closed universe, parallel lines converge. Now, the weird thing is that that's an unstable point. If, as the universe evolves, you move further and further away from 1. If you're a little bit less than 1, then pretty soon you're a lot less than 1. If you're a little bit bigger than 1, pretty soon you're a lot bigger than 1. In fact, it goes so fast that we know that we would have to have been extremely close to 1 in order for the universe to even exist today. It should have either expanded so fast, no stars, no galaxies, no nothing, or collapsed back into a black hole before you could sneeze. It didn't. In fact, what we measured is that it's very, very close to 1 today, which means that it had to be insanely close to 1 at the beginning, and that is one of the kind of mysteries in cosmology about how do you get it to be just right so the universe keeps working. Now, there's some models, and one of them is that somehow just shovel in a new hole full of magic, and you have this thing called inflation, which causes the expansion of the universe to expand exponentially, extremely fast in the early universe, and then stop for some other magic reason. And in doing that, you can make the universe appear flat. But if that happened, it should produce gravitational waves that would have been emitted at 10 to the minus 30 seconds after the Big Bang. So 0.0301 seconds after the Big Bang. So that's what I'm working on right now, is a telescope to look for those gravitational waves that could maybe explain this flatness problem, but they might be too small to measure. But it's worth a try, right? If it's there, it'd be cool.
So as you explain this stuff, and like when I look at this kind of stuff, I mean, even just going onto YouTube or something and seeing some of what you see just in terms of the magnitude of the size of it all.
Yeah.
Like, I'm just blown away by it. It's one of those things that's just mind-boggling.
Yes.
Do you still have those experiences? Like, because I'm a theologian, so I'm not discovering this stuff every day. But do you still get those moments as an astrophysicist that are just shocking, surprising? What are some things that have surprised you, if so?
That's a funny thing, right? Because you can sit and do astrophysics all day, and as long as you use scientific notation, it doesn't seem that big.
Yeah.
10 to the minus 30, that's easy. I just said it. It's like a mind-bogglingly small number. 100 billion stars. Oh, I just said that number. Well, how many is that? That's the number of grains of sand in a dump truck. Huh. That's how many stars in our galaxy. That's a lot. But you can spend all day not thinking about it until if you had to find a particular star in a galaxy, you never could, right? If you found yourself in our galaxy, you could never find your way home. There's just too many stars. In real life, in day to day, I'm like trying to figure out why the calibration on the thermometers and on the payload is wrong, or what's this vibration coming from the pointing motor?
Yes.
So you just have to stop sometimes and think about it.
Mm-hmm. Yeah, be conscious of it.
So I don't think I have any special access to that.
Yes.
I think any of us can think that way too.
Sure. Now, I should say, by the way, for those of you here tonight, if you're not aware of the documentary called Blast, you should take a look at it. It's about an hour long. It's really good. It really gets you into the day-to-day life of the kind of stuff that Bart and his team do. One of the things that really struck me, and I was saying this before when we were chatting, is, like whenever you hear about astrophysics and astronomy and so forth, it all just seems so big and so abstract, and mathematical, and it is all that. Mm-hmm. But what really struck me in the video is just how bodily, this kind of work is. I didn't know how involved it was, just in terms of you guys build stuff. So you don't just contract all that stuff out. You build stuff in order to do all this.
They don't grow on trees.
They don't grow on trees. So what's that like? You're employing students to do this? Do you do a lot of this yourself?
Yeah, I do as much as I have time for, which is not as much as I'd like.
Sure.
But mostly the students do it.
So they're actually building the materials and the...
Yeah.
Incredible.
They spend time in the machine shop and with the soldering iron and the wire strippers and and the wrenches and make it happen.
So there's a real physicality to this.
Yeah.
And then, when you're out on the field, what's that like? What's it like to walk on the surface of the Antarctica? I mean, it's cold, obviously, but
actually, we're there in the summer.
Okay.
So McMurdo Station is the farthest south that the sea ice melts. So it's the farthest south they can take a ship to replenish. That's where they put the base. And so what that means is in the heat of summer, it's just around 0 C. So so when you first arrive in October, November, it's 20, 25 below. Okay. It's cold, but, and then it just gradually warms up.
Gets to a nice balmy 0.
By the end of the season, I have my jacket unzipped part way. And
That's interesting to know, because I lived in Manitoba, Winnipeg the last 6 years, and so we get minus 40 below. So
it's South Pole we get minus 40.
Yes.
I've been there once, and that's awfully cold. Yeah. It's like Saskatoon, which I spent a few winters in Saskatoon.
Yes.
The other way to get rid of water vapor is to get really cold, and a really good way to get really cold is to go to Saskatoon in January.
Absolutely. So. And what size of a team do you have down there?
The total team for most of our projects would be between 15 and 20.
15 and 20.
It'd be probably 6 or 8 from Toronto. Yeah. And then the other universities.
One of the things that struck me on the video too is that there's all kinds of things that can be hiccups, right? Mm-hmm. You I don't know how many launch attempts or days that you hope for, and then you end up waiting. So how long in total are you there?
So typically we head down the last week in October and fly home in the middle of January.
That's a pretty significant time investment then.
It is.
Yeah. And fairly isolated. Can't go home on the weekend.
No, I've missed several Christmases, shall we say.
One of the other things that I found really fascinating.
So one year.
Yeah, go ahead.
Yeah. My son had me on Skype on the Christmas Eve service and just carried me around the church so I could say hi to people. Oh, hi. That was great.
That's awesome. Now, it must get lonely, though.
You're working so hard that it's...
Go.
Yeah.
Yeah.
And I really appreciate my team. They're great people. So
excellent. One of the other interesting themes that comes out in this video is there's this kind of theme of faith that gets woven into it a little bit. And I found that interesting. I also found it interesting because if you go online and to order it, you can order the version that has that content, and you can go to a version that has no references to religion, which is kind of interesting.
Yeah, if certain high school teachers wouldn't want that.
Yeah, so it's available in both, right?
Yep.
Yeah.
Yeah, but obviously the versions that were shown on Discovery Channel and PBS and stuff had it.
Yeah. So as I saw, and Barth's a major part of this video. It's a very important project, and it struck me that you seem to be fairly open, about your own faith, and not in any way that's sort of forced or anything. But I mean, there's a couple places where you're just reflecting on the beauty of it, the wonder of it. Are you usually like that?
Yeah, I mean, I'm pretty open about my faith with my students in the lab, and
You're allowed to do that?
of course, why not?
Oh, I don't know. Yeah, that's interesting.
What do you mean, am I allowed to do that?
Be open about your faith in the context of,
Why
of a
not?
university setting. Well, I don't know. I'm just asking.
Well, there's a difference between being open and saying, if you want a good reference letter, you better convert.
Right. Exactly. Yeah. Well, I just found that very interesting and kind of attractive, the way that you talked about that. So what are some of the big kind of God moments for you as you've been in the laboratory or on the field?
Yeah. So when I was a teenager and in junior high and high school, my grandfather lived with us, and he was a retired pastor. And he told me, Bart, you should go into science. You'll see the glory of God. I was like, okay. Now, in those days, of course, evangelical churches had a sort of dim view on the Big Bang and science and evolution. And I was like, oh, that sounds kind of scary. But all truth is God's truth, right? So it has to be true that if I'm studying truth, God will be glorified, or there's no God. And it would be foolish to avoid it. What is that trying to say? I don't have, right? So I decided to go. Now, in parallel with this, my dad was also a pastor. And I remember he had Bruce Waldke from Regents come out and give a Bible study for our church, a series. And I had some conversations with him. And it was amazing to see that here's this theology professor, Old Testament scholar, brilliant man, basically saying, you can't really understand the age of the universe from the Old Testament. It wasn't trying to get at that. The people who are claiming the universe is 6,000 years old from Scripture are misusing Scripture. That wasn't the point. And I was like, well, this is reassuring. So off to college I went. My intention was eventually to do high energy theory, not really astrophysics, not really cosmology. I was all set up. I was going to work doing high energy theory. It was going to be really cool and interesting because I did a bunch of lab work. It's fun, but that's not what I'm going to do. I had a job going to be doing computer simulations, actually with a cosmologist. It's like, well, okay, that's okay for a summer job. I got a phone call from him right before I went off to grad school. He said, you may have heard in the news that the Hubble Space Telescope is out of focus. So I'm going to be in Washington, D.C. for the next year in meetings, so you have to find a new advisor. And the job that was open was in the Cosmic Microwave Background Lab, looking at radiation from the Big Bang. I'm like, ooh, that's sketchy. But I'm going to do this. And I think God just kept nudging me. No, this is where you're going to go. You have to go here. And it was just it's been an amazing experience, just seeing how God shows himself through creation in this way, in a way that only God can.
Yeah.
And not in a way that I would have done it, because I don't have enough imagination.
So this idea that
all truth is God's
truth is God's truth, and so if we discover truth, it shows us something about the
Him.
Creator.
Yeah.
Yeah, That's fascinating. Very good. And there was a bit of resistance in that to you at first, you're saying, that
It just seemed a little sketchy.
Yeah.
I wasn't sure, right? Because you grew up with this sort of feeling that maybe I should be nervous about this, you know? Like, no, don't be nervous. Just do it. You'll see. You'll see. Trust me.
Very good. Were there other challenges along the way? Any things in science that you? I mean, and sometimes it's not even the things we struggle with. It's in the context of, let's say I'm a scientist and I'm also a Christian, and I'm learning stuff, but I'm not sure how to communicate this with others. Did you have those kinds of experiences where you're kind of growing into this and you're either wrestling with something you've encountered, or you're not sure how this works in terms of others around you who are church people, let's say?
Well, not long after I got into doing this work and really getting into it and understanding how it shows God's glory, of course you start interacting with, I have to admit it, other Christians who say, man, you don't have any faith, you don't believe the Bible. And that was hard. That wasn't the funnest thing.
Yeah.
Especially when I'm a young grad student and an elder in the church is kind of a man I otherwise respect. That was tough.
Yeah.
Haven't had much from unbelievers, especially in my field.
Yeah. Because
I think people in cosmology know that there's some pretty serious unsolved problems that give them pause. Like the fine-tuning thing is big.
May have to unpack that just a minute. Fine-tuning,
so
what's that about?
The point is the universe, there's a whole bunch of numbers that go into the model. The density of the universe, the expansion rate of the universe, the strength of the strong force and the weak force and the gravitational force and the electric force and the mass of the fundamental particles. And there's all these numbers. And it turns out that if you change them, even a little bit, the universe doesn't work. Like you can't make any nucleuses heavier than lithium in stars, so you couldn't have life. Or the universe would expand too fast to create stars at all. And it goes on. And there's all these numbers, and they have to be exactly right. And if you change them, and there's no reason to know why they are what they are. And so you end up with this fine-tuning, they call it the fine-tuning problem. And it's a problem. And so cosmologists, when I talk to them, I've never had one of my colleagues say to me or imply to me, oh, believing in a creator is dumb. It's not something they think or say. They might have problems with Jesus, but that's the problems that anybody
so like
have.
A religion in particular.
Yeah.
Yeah.
But like creator, oh sure, I get that.
Yeah.
I don't think so, but I get where you're coming from. But it's a really funny business because I don't want to be in a place where my faith is based on not understanding physics.
Yes.
Right? It's like, I finally understand this weird problem. I understand how fine-tuning came to be.
Right. So we keep God for the things we don't yet understand.
Yeah, and that's not right.
Yeah.
I believe in God because of what he's done for us, because of his son, because of the resurrection. And then I learn about him through science. But I don't prove him through science. I'm just seeing how the universe behaves. The universe that he created, it's his. Yeah. And he could have done it however he wanted.
Sure.
And I think what we find is, I don't know, it's this kind of picture. So imagine you go and you watch Lord of the Rings, and there's this gorgeous, beautiful castle. Like, Minas Tirith or something, right? And it's like, oh, wow. And it's like, that's really beautiful. And Peter Jackson said, let there be Minas Tirith. And a bunch of guys with computers typed, and there it was, right? That's not how God did it. God says, let there be Toronto. And there was a big bang, and everything happens to make Toronto with a complete backstory according to the rules. I can imagine Toronto by fiat. But what God actually did just baffles me. How could you get to here from there? using these simple rules. But you did.
Yeah.
And it's absolutely astounding. And so in a sense, as we understand physics, God just gets bigger. How in the world did you do that?
Yeah.
Not, oh, that's all you did. Like, no. It's quite the opposite.
Yeah, yeah. Yeah, that's fascinating. And it's funny because sometimes, yeah, you go ahead.
So, sometimes you hear people say, oh, we understand chemistry and physics and whatever else. We don't need God anymore. Okay, so it's like this. People sitting around, some literary critics or something, are sitting around, they're talking about Shakespearean sonnets. And a new guy in the group says, I find it really fascinating how Shakespeare, and the other person interrupts, like, Shakespeare? That's so old-fashioned. We don't need to invoke Shakespeare for the sonnets anymore. We understand the rules of Shakespearean sonnets, the rhyme, the meter, the parallelism. Why would you invoke a poet? He doesn't need a poet. We know the rules. Same with physics, right? It's like, oh, we understand the rules. It doesn't make any sense.
Yeah. Well, that's fascinating because a lot of us do think of physics as a bunch of calculations and rules, but there's a history here. Like you're into, this is getting you into a history, a story, in a sense, right? Of where we've come from.
So God creates the universe using rules in the same way that Shakespeare creates his sonnets using rules, because it's cooler, because it's better, it's more impressive. Like anybody can just write down random words, but to give it the art and the structure and the style, Shakespeare said, this is the way I'm going to do it. And same with God. He's like, I'm going to use, the poetry is so much better if I use work within this structure. It's like, wow, it's really amazing.
It's fascinating. So the detail matters, and that complexity and even time, right? Like I think some Christians, some of us have struggled, or maybe some of us still do, with this idea that it seems just more majestic for God to do it like instantly and fast and big and now.
I don't see that.
Yeah, so that's a choice we make. That's a preconception, I guess, that can stump us
when you
up.
start to realize, no, he didn't just call it like Peter Jackson would.
Yeah.
No, he did the whole dang thing.
Yeah.
And he actually had an entire history of the elven world in order to get, Peter Jackson could never do that.
And I mean, maybe it threatens our sense of self or something, right? Like we think that, what's really important is us. And so what matters is the time that we are really important. But to think that God, for 14 billion years is watching all this unfold.
I think we're only really important because God is infinite and has infinite attention.
Oh, wait a minute.
If God was finite, I think he wouldn't notice us.
That's interesting. Say more.
Well, the universe is so big and there's so much. If God was finite, he couldn't even find us.
It's incredible.
I don't know. Yeah, the universe is huge. The existence is huge. So we think that the universe is possibly/probably infinitely large. So no end. Go on forever and keep going, and there's just more universe to go, more stars. How many stars are there? An infinite number. There's a mind-boggling number of stars in our galaxy. That was the 100 billion, the number of grains, right? We can see from Earth about 1 trillion galaxies. So that's the number of grains of sand in 10 dump trucks, right? So each grain of sand, you pull it out, and you realize it's a dump truck full of sand. And each one of those grains of sand is a star, okay? So that's what we can see from Earth. We can't see further than that because, as we said, the further away you look, the further back in time you look. So if you try to look any further, you'd be looking before there were any galaxies, so you can't see them. If we wait, we'll see them. Like, wait another 14 billion years and you can see even more, but I'm kind of, okay, right? But if there's an infinite number of them, well, how many planets are there? Well, infinite number. How many planets with life on them? Well, an infinite number. How many planets with intelligent life on them? Well, an infinite number. How many planets with intelligent life, with astrophysics professors talking to theology professors at a university called University of Toronto? Well, I guess an infinite number of them, right? So how important are we? We're important because God is infinite and he cares about us, but it's him that makes us important, not us.
Yeah. Well, on a totally, well, maybe not unrelated, but I've often stopped and thought about, how complex and intelligent and sovereign and huge God must be to interact with the prayers of 6 billion people simultaneously. And it seems like this is just kind of another version of that in a way.
Yeah, because but it's him, not us.
Yeah. Very good.
If it wasn't for his nature, we wouldn't be important.
Well, let me loop back to your time in the South, in Antarctica. Because here you are down there, you're in a project with 14, 16 people whose lives are deeply invested in this, whose PhDs are riding on this. Lots of money been poured into this technology, satellite, planes, everything that goes on here, time away from family.
Yep.
And you guys almost lost the data.
Yeah.
Can you tell us about this? This is fascinating.
Yeah. So in 2000, we applied for money to build an experiment called BLAST. And the goal of it was to look at the star formation history of the universe. Basically, when did stars form? That was one of the questions. So we got funded to build it. We took a few years to build it. In 2003, we went down to New Mexico and did a test flight of it. That worked okay. So then we went off to fly it from in the north, from Sweden, and that flight did not work because the telescope was out of focus. There was a problem in the way it was built. So now we've been working on it for 5 years. Students are expecting to have data to write their theses, and they can't. It landed, we got it back. It's like, hey, we're gonna turn it around again and take it down to Antarctica. Got it repaired, got it upgraded, fixed the mirror, figured out how to get it in focus, headed down to Antarctica about 18 months later, finally flew it down there. So that's now been 6 years. And students are starting to think, what happened to my 5-year PhD? Get down to Antarctica, get it put together, and launch it. And we get to float, and the telescope is working really well. Now, the telescope accumulates data at around a megabit per second, and our link to the ground is like dial-up. It's like 8 kilobits per second. So slower than dial-up.
It's like a fax machine.
Like a fax machine. You get 8 kilobits per second downlink from the payload. We're collecting a megabit per second. So basically all the data is stored on disk on the payload. And the day before the launch, on the day of the launch, I was doing something and I said, to my collaborator, hey, can you tie the computer down to the deck so it doesn't fall off? I've been meaning to do it. We hadn't done it yet. Okay, he said he would take care of it. I come back from whatever I'm doing. We're rolling out the door, and I'm like, hey, you didn't tie that down right. It's just on these flimsy little sticks. It's gonna come off. He's like, no, it won't. It's like, it's gonna come off. It's like, we got to retie it down. It's like, no, we don't. We're launching. He was the USPI, and he's bald and means it. So we launched, and so the whole flight, I'm like, the knot in my stomach. What if the data vessel comes off when the parachute opens, right? So I'm just a bit nervous, but nonetheless, beautiful flight, few adventures, We're getting ready to end the flight, to bring it down in parachute. It's a good location. They've scouted out, we can land a C-130 here to pick it up. It'll be fine. At that point, I made a questionable decision. Not really. I'm saying that because it's funny. I prayed that God would glorify himself in how the recovery went. Kind of an open-ended thing. So God, do something awesome. Do something awesome. Parachute opens. It's coming down. We're hearing about it over the radio. It lands. Okay, so we need to do an aside here. Antarctica is a place, not just scientists go there, but also adventurers who want to do adventures, right? So at this year, there was a particular team who decided they were going to parasail across Antarctica. Right, so you have skis and like the sailboarders, but with skis.
Oh, yes.
And this is like in the early days of the internet-ish, and they have Iridium data link, Iridium dial-up, and so they have their blog going, and they're complaining that there's no wind in Antarctica, and this is a terrible idea.
Just come to Manitoba.
Yes. They were on the far side of the continent from us, however.
Yes.
Where we landed, there were 20-knot winds. Well, okay. Well, so what's supposed to happen is the parachute's come down, it's supposed to land, and as soon as the payload hits the ground, the guy in the airplane hits the red button that fires a little explosive bolt that releases the parachute. Wind catches the parachute and starts dragging it across Antarctica. And so we hear over the radio, the payload's dragging. They come back a few hours later. They showed us the picture. They circled it for about an hour, and then they had to come home. The payload, parachute, 120-foot parachute, completely open. A furrow behind our telescope across the ice, heading off to who knows where. Okay. Answer to prayer. Maybe, right? So the next day, they sent out a small airplane with a couple observers to go look for it. They're gone all day. They finally come back at the end of the day. They're exhausted. They said, we'll tell you what we saw, but we need to eat first. So we're just like dying. And they come over, okay, here's what happened. We followed the payload. There's a few places along the way we found rubble had just broken off the payload from being dragged in. And there's like, okay, there's our flight computer. There's our data computer, and there's our mirror, there's the cryostat. And the whole thing dragged 135 miles until it came into what's called a crevasse field. So what happens in Antarctica is where the ice flows from the plateau down the Transantarctic Mountains, you get these cracks in the ice that are about 1 kilometer deep and about 15 feet across on the surface. But then wind blows and makes a little ice bridge across them. If you walk on it, you'll just fall 0.5 kilometer. And the payload dragged until it got to one of those, fell into it, and got wedged halfway down on the side. And so there's a picture of our payload stripped of everything, wedged into the side of this.
This is a very precarious place.
And looking at the pictures of the environment, it's like, you can't go there. There's crevasses everywhere. Oh, man. And so I went to the station manager at McMurdo in the base and said, listen, we want to go try and find our data. Look, in the picture, it wasn't a great picture, but it didn't look like the computer that was supposed to be there was there, but we didn't know. We had to find out where it was. So we need to go out again, we need to survey the area. And he says, okay, well, there's this, it was a converted World War II DC-3 that they could let us use. They were going to be going and refueling, bringing supplies to a field camp, but they can wait, they don't need more food, they're fine. So they let us use the plane. So that night, that was a hard night. Because 6 years of work in the balance, right? The payload is completely destroyed. We won't be able to refly it. So it's just like everything I've done as an assistant professor was this project. My students all need data. I've made statements about God glorifying himself. And now what? Like, it's all gone. I was staying up that night and praying, and I remember reading not necessarily very comforting words in Jeremiah. Don't pray for these people because they're going to ignore me anyway. It was kind of the picture. It's like, So I didn't know. Like, this was hard. This was a dark night. Next day, we get up, get on the plane, head up over the Transantarctic Mountains, fly over to the place where the payload is. I'm taking pictures with the telephoto lens out the window. And I zoom in, it's like, the computer's not there. It came off. Got to step back a bit. Talking to the guy who runs the base, the station manager for the National Science Foundation, he says, so what is it that you're looking for? Well, it's a pressure vessel. It's about this big and this big around. Okay. What color is it? Well, you see, you want the flight computer to cool, so it needs to be emissive in the thermal infrared, but you don't want it to absorb sunlight, so it needs to be reflective in the visible.
Oh no.
It's white.
Oh no.
It's as white as we could make it.
Of course it is.
So we're now going to be looking for a white tube this long and this big around somewhere in Antarctica. Now, and it doesn't look like it's on the payload anymore. It had gotten wedged in a way that we could see that it wasn't there. So we're flying along, coming back to make another pass of it for more pictures. And the pilot says, I see something on the drag line. And out my window, phew, that was the pressure vessel. I'm sure of it. So we go around, we fly back, and what do you know? Took pictures out the front window, zoom it in. There it is, just sitting on the ice.
Oh my goodness.
It had dragged 132 miles, still attached, and when those screws that I was so worried about vibrated loose, it fell off 3 miles before the crevasse field.
Oh my goodness.
After dragging 132 miles.
And that's all your information there.
All
your
of it
data.
was there. And it was in a spot where they could land the Twin Otter, pick up the data, and bring it home. So that was God glorifying himself. Wow. Not how I would have planned it.
Very good.
And it was great. Ended up with a nature paper and a documentary, and I don't know, we had over 1,000 citations from that flight, and it was good. It turned out really well. Discovered there's this glow in the sky in the infrared that nobody knew what it was from. Discovered where it came from. It comes from star-forming galaxies. That was cool. So there we go.
Thanks for sharing that with us. That's incredible.